All right. I guess we should get started because we're a little bit over time with the last but not least session for today. And the first speaker is Saul, who will talk about the Hyper-K experiment. So take it away.
Vamos a ver. Ok. All right. I hope I'm not too loud. Well, a little bit. Uh, Thank you for the introduction, Dennis. So I'm very happy to be here and to talk to you about Hypercake experiment and the Mexican contribution so far. Uh, so here we go. The agenda for today, I'll mainly talk about Hypercake project goals and status, and I'll also talk about a little bit the uh, work done at here at Mexican universities. Here's a small ad for the HyperK official webpage and another ad for the outreach page for Mexico. So if you want to follow Señor Neutrino, please go ahead. Yeah. So most of you most likely know, but I'll introduce this formally. Hypercamiocande is a project that would include a far detector, a neutrino beam, and a neutrino new detector complex. So here's the islet of Japan. On the East Coast, we have J-Park, so it will shoot a neutrino beam all the way to Kamioka, where the far detector will be. Is currently under construction. And near J Park, we have the famous ND280 and Ingrid used for Super K. And part of the program for Hyper K construction, another new detector will be constructed, IWCD, which will be very helpful to mitigate systematic uncertainties. Also, you may know, this is the third generation of Kamiokande. The first one from 83 to 96, very famous for doing atmospheric and solar neutrino anomaly discovery, I guess it could be said. Also, the observation of supernova 1997, and this gave birth to neutrino astrophysics. Super K, since 96 and still ongoing, has the best proton decay limit, and it measures neutrino oscillations for atmospheric, solar, and long baselines, measuring all mixing angles and the mass difference of the neutrinos. They're very famous for doing the discovery of neutrino oscillations, and you can see here was the formula. Just keep getting bigger, right? But it works. It keeps giving results, so I guess we'll keep doing that. So Hyper-K, it's set to start around 2027, 2028. And the main science program is for doing extended search for proton decay and keep doing precision measurements for neutrino oscillations to the precision region. So this will include studies for charge parity violation and finally set up the mass ordering of the neutrinos. Additionally, there will be a lot of neutrino astrophysics going on that will be very appealing to most of the audience, and obviously explore new physics. So this target, it will be very useful. It will be sensitive to supernova neutrinos within 10 kiloparsecs. It will be sensitive, obviously, to solar neutrinos. It will be sensitive to atmospheric and long baselines, as I described. There's some decay channels here, an example. And one of the possible discoveries will be the decay of the proton, right? There's several theories that tell us that this might occur, and the theory tells you that it may decay to a lepton and a pi zero. So the proton will spit out an electron or muon, and the pi zero will convert to two gammas, and that gives you a very nice signature for this discovery if it ever happens, right? So we will be very we will paying attention to this signal a lot. Okay. Uh, again, a lot of people may know this. How the experiment works. What is the technique? The technique is you have a very well known neutrino production line, and you have these very nice new detectors that tells you the cross section and the beam composition. You shoot that at 300 kilometers, and for the energy that you're shooting and the baseline for that gives you the maximum oscillation probability. And then since you know how the neutrino looks at the beginning and at the end, you can tune in the parameters for these famous matrix, right? You have the angles and the CP phase and the masses of the neutrinos. You can reconstruct the energy so you can get a very precise prediction measurement of the oscillation parameters in the mass for masses. Uh, what will be the sensitivity to Hyper-K? Hyper-K will have sensitivity in different physics categories. For long baseline, as long as J-Park reaches 1.3 megawatts over 10 years, the CP violation precision will be between 7 and 20 degrees. The CP coverage will reach 5 sigma and excluding almost 60% of the range, which I will talk more about this later. Also, these angle 2-3 will be measured to a very precise number, 0.001, more or less. For the atmospheric and long basement category, we will have mass order determination to almost 4 sigma within 10 years. Again, precision measurement for this angle 2-3 to 2 degrees. For the proton decay program, so in 20 years, we will have a 3 sigma limit for the pion zero decay channel. We will put a limit.
Excuse me, Professor.
What was
Can I
that?
interrupt you? Can I interrupt 1 minute?
Oh, I guess so. Yeah, go ahead.
What is the exact value of proton life period?
Could you
It
say
was 10 to the power of 32 years predicted, but now what is the value?
20 years? Uh, you will
No,
have
proton life period
uh-huh.
previously predicted 10 to the power of 32 years. But now what is the value prediction?
Well, the prediction is right here. 10 to the 35. That will be the half life of the proton. I can get back to
Well,
you offline, and I can just show you where that is in the article. No problem.
okay,
Right,
thank you, Professor.
yeah, thank you. For the ODK channel, for the counts, it'll be a little bit lower, 10 to the 34. For the solar neutrinos, within 10 years, we will have very good measurements for the day and night asymmetry, you know, when it shoots from above and from the bottom. A very good precision. Also for the upturn, which I will talk more about later. And for supernova, burst supernova within 10 kiloparsecs, the experiment will collect around 70K neutrinos, which is pretty good. And for relic neutrinos, I'm not sure what's the mechanism to detect this. And the collaboration claims that they will have 17 neutrinos in 10 years. Since for what I know, these relic neutrinos are very, very low energy. So I'm not sure if we're going to be able to detect them or not. Okay. For the long baseline program, with the help of J-Park neutrino beam, it will be a 2.5 off axis angle from J-Park to the far detector, and J-Park will be shooting mu neutrinos and T-mu neutrinos, and the beam will peak at 0.6 because when you do that at 295 kilometers, you have an oscillation maximum over here. So that's what we're looking for. And the energy of the neutrino will be determined by the momentum of the angle of the sharp lepton that is initiated in the tank. Okay, so how do we do this? So we measure CP violation neutrino by comparing the probabilities of mu neutrinos going to electrons or muons going to anti-electrons neutrinos, and you compare that, right? And you construct the cross sections and you extract the CP violation term from there. Okay, So according to predictions, in 10 years, we will have more than 10,000 neutrinos and antineutrino signals. For the CP violation sensitivity, we are predicting that in about 2-3 years, we will have a 5 sigma measurement for if we have a true delta CP of minus p/2. If the value is more close to minus p/4, it will take us longer. It will take us about 5 years to reach 5 sigma exclusion from almost 60% of the angles, right? So that's why it's like this over here. So it's 5 sigma. Most of the region will be excluded for CP violation. It will take us about 2 to 3 years to reach 5 sigma sensitivity to mass ordering. And yeah, more or less. For the neutron decay search, so there's evidence or theories beyond standard model and GUT for these decays over here, proton to decay to the pion 0 channel or the proton to the kaon channel. And here's a comparison between HK and Dune. Their sensitivities over 10 years. If there's someone from Dune here, I'm sorry to do this comparison. It's just how it goes. And again, for the other channel, for K plus channel, also hyper K is predicted to have a world leading measurement. For neutrino astrophysics, again, hyper K is designed to be sensitive to neutrinos with energy in the few MeV. That's the energies where the range energies you get from supernova bursts. So we will have time, energy, and direction information from those events, and this will play a unique role in multi-messenger observations. For the solar neutrinos, we will study the upturn. So the upturn, it's the slang for the transition between vacuum oscillations and MSW transitions. So you can see a plot here, and there's a lot of uncertainty in this switch. So hyper K will try to measure this to a better resolution. Also, another focus of the experiment will be to study supernova burst neutrino, the explosion mechanism, the black hole neutron star formation, and we will have a sensitivity of 1 degree. Again, we will study star collapse and nucleosynthesis, the history of the universe. Great. Hyper K, it's a big collaboration of about 600 members, around 100 institutes, and it recently was approved as a CERN experiment, as quoted over here. And we were very happy to have a first in-person collaboration last year again after COVID. So collaboration is open for new collaborators. If anyone wants to join, now is the time, right? We still have time to join. The schedule goes from 2020 to 2028. Right now we're here. We're currently doing the cavern excavation and it's planning to be completed by 2026, so we can start the PMT installation. There has been going on production of PMT since a couple of years from Hamamatsu. Also, the PMT covers and electronics are being developed right now. The water system is going to start to be installed within these or the next year. And then by 2027, we will start the water filling. There's have been slow but steady progress on J-Park upgrades. So we want to reach 1.3 megawatts for the main beam. And also in parallel, there is the construction of this new detector IWCD, which will be very helpful to mitigate uncertainties since you're going to be able to move the detector at different depths. So you can reconstruct the probability for different angles. Again, some update on the excavation. It claims to be the world's largest human-made cavern, and you can see here the map here's the detector. Is gonna be about, I don't know, probably 600 meters below the peak of the mountain. The access tunnel was already completed a couple years ago. Here you can see a top view of how the chamber is gonna look. And you can see how it compares the new Hyper-K cavern against previous detectors. Yeah. This is a very impressive picture. I'll be a little bit scared myself to be down there. And here I'm showing that the main cavern, it's already finished. And but it's not done yet. You still need to do the barrel part. So that will be done within next year. So people are still working on this big excavation. It's hopefully will be completed next year. Yeah. Okay. So how does it look inside? You know, the inner detector. The inner detector. This is just a small section here. This small section is gonna be like multiply lots of times, right? Round and up. And mainly you're gonna have three types of detectors. The classic one for Super K is a 50 centimeter PMT, right? So that's the one in orange. And there's also gonna be these other called multi-PMT detector, which is becoming quite famous for different collaborations. I think this idea was took from Chem3net. They have something similar, so they adopted this type of geometry. It seems to be very good for the analysis. Why? Because you have 19 different PNTs looking at different angles, and that gives you a lot of information when you do the analysis. It can tells you, it can give you a better angle direction from the incoming beams and so on. Yeah. Anyway, so those are two types that they're gonna be looking into the detector, and there's also gonna be these cylinders here. The cylinders is gonna be electronic converters and digitizers, because from Super K experience, they have a lot of cables, and that's very cumbersome. So they plan to do less cables by doing the most of the analysis within these little frames that I'm showing you. Okay, so we're gonna have around 20,000 of those classic PMTs, if you wanna call them like that. There's gonna be around 800 multi-PMT modules. And for the outer detector, if you pay close attention, there's this type of squares at the other side, right? That's the outer detector. And we're gonna have around 3,600 3-inch PMTs, which we're gonna use to do BETOs and some other background rejection. Yeah. So what's new about these detectors, these PMTs? Well, now this new model is gonna have 2 times better photo detection efficiency from Super K, and is gonna be 2 times better at detecting charge resolution, and also 2 times better timing resolution. And again, this experiment is just an improvement of Super K, right? We're trying to reach the precision era, not just looking at stuff. Yeah. This is a very nice picture of the PMT production, which is ongoing. 10K have been delivered already. That's half of the production of those. And they're currently being screened at both Hamamatsu, the company, and Kamioka. And it's pretty impressive to look at all these devices. All right. I already explained you more or less what the photo sensors are gonna be like. This is just well, a closer look at how these outer detector PMTs looks. They're very small, just 3-inch PMTs, and they're gonna have these nice wait, this wave shifter plate to just maximize detection. Again, this is the mock-up frame for a regular 50-inch PMTs, the multi-PMT here, and here is supposed to be the underwater electronics, which will help us to do less cables overall. It's just some testing, submerging the electronics underwater. Here's how the cover will look for the 50-inch PMT. Most likely, most of you know that there was a disaster in Super K many years ago, right? They had one of them exploded, and there was a cascade of explosions. And then after you know, here in Mexico, we have a saying: after the child was drowned in the hole, then you do something about it, right? So they had to do that, and now they don't want to risk it. They're gonna put covers since the beginning, right? The multi-PMT device is this one here. You can see this 3D model. So you have 19 PMTs looking at different directions, and well, that already told you that gives you directionality about the event, which is really precious information. Uh, HyperK is going to use a lot of calibration systems, but they're very important so we can have a good measurement, a precise measurement. Among them, there will be these photosensor test facilities so we can test each PMT or most of them before we put them in, characterize them, and pre-calibrate them. There's also going to be this very nice technique that I like a lot. It's called photogrammetry. So we're going to have cameras looking at all directions so we can know exactly where each PMT is. So that will give us a lot of sensitivity. Again, I'm going to start to speed up because I'm almost out of time. So I'm going to start skipping a couple of slides, sorry. The beam status, I already talked about a little bit. Just a couple of weeks ago, 800 kilowatts was reached, and the goal is to reach 1.3 megawatts. How is this happening? Well, different reasons. The beamline is being upgraded and so on. The need detectors, I'll skip this one because I already talked to you about this a little bit. And then finally, I want to use, we're very proud here in Mexico that we finally got some funding to join the project, and there's other scientists here that they're part of the team. Eduardo, right, the organizer, or our guy, right, is leading one of the grants, and myself as well. I'm doing one of those. There's also Karen, Janina, and Katsumi over here. Very good job, yeah. And we're gonna do an MOU between U Tokyo probably this year, and we're very excited about this. What have we done so far? So we have we're very proud also about Maria Fernanda. She gave a talk yesterday about their thesis on neutrino classifications. That was very nice from her. We have another doctoral thesis is still going on, also about doing machine learning for classifying neutrinos. And there's open positions now for different subjects for me and other professors, so people can look at them later. I'm gonna skip this slide. Maria Fernanda already talked to you about this. And we're studying multi-PMT prototyping in Mexico. We have several students here working on constructing the multi-PMT mechanical devices. We'll also start doing some PMT characterization. So we're building up in order to also the Mexican community wants to install around 10 multi-PMTs in the tank. That's our goal, and we're working towards that direction. Also, we were also trusted to develop the multi-PMT support basis. What is that? So you have the multi-PMT or the detector. You want to put it into the wall, right? So you need something in between. So we were doing that ourselves, and we have very precise requirements such as the weight and the type of the material, because it's going to be submerged for about 20 years. We also did a lot of mechanical stress testing on the detector. This is a laboratory on one of the universities over here in Mexico. We did compression tests, humidity tests, and a bunch of required tests that need to be part of this. So this effort that we did in Mexico for the supports, they were actually used in the mock-up test done a couple of months ago. So they were able to use our supports and part of the multi-PMT design that we did as well. So this happened a couple of months ago, I told you. And this is a very happy scientist, one of my friends, collaborators, right? We're very happy that the mock-up test was successful, and we're working into that direction. Yes. And I think I'm done. Oh, well, the conclusions. Just to close it up, HyperK is going to be a third-generation water Cherenkov detector in Kamioka. The important physics target, it's the neutrino CP violation discovery with 5 sigma for 60% of the parameters. Nuclear indicator search for the for the two channels that I mentioned, and neutrino astrophysics. Hypercamiocan, the construction is on schedule, but with the world largest underground facility with 260 kilotons of water Cherenkov detector. The axis and the tone, the cover now on track. Detector components are being finalized, and yeah, all of this already mentioned. Thank you again for listening up. Yeah.
Many thanks for the nice talk and for staying in time. You actually had 20 seconds left, so you're good. Are there any questions or comments? Karl-Heinz, I think.
Yeah, so that's really aggressive time schedule. I mean, in 2 years from now, I wish you good luck.
Yeah. Well, you know, people always say, "Oh, we're gonna do it in next year," and it always takes a couple of years. Yeah, it's how it works.
My question is, how much can Hypercamera do on the mass ordering, on the mass hiring by itself? I mean, I understand they will take it from you in a way, but you can also constrain it yourself, right?
The experiment itself will be able to do it to some degree of certainty, but I also agree most likely there will be a collaboration and there will be shared data between a bunch of long baseline neutrino experiments such as Dune, maybe Nova, and
Yeah, yeah,
anyone who wants. They do an analysis all together, right? That's the usual way to do it. Yeah, for sure it will happen. Yeah.
Okay.
Yeah.
I think Ralph had a question. Right?
I'm not sure, but so first of all, thanks a lot for this very great and enthusiastic talk. But wasn't initially a plan to have Hyper-K being several of these volumes in the mountain and not a single big one? You know?
Yeah.
That's
I remember that old document. You know, they even said that they wanted to construct another one in Korea and have a second oscillation, right? And
Yeah.
put that all into perspective. There also was a model to instead of only having one, to do two. It looked like a
Exactly, yeah.
spaceship, right? You probably look at the picture of the figure.
Mm,
Yeah, but it just didn't happen, right? They always, you know, now it's secure to do 20,000 50-centimeter modules, but a couple years before that, they said we're gonna do 40,000. But you know, as funding comes in and reality kicks in,
Yeah.
just that's what
And
happened.
are you going to run with just with purified water, or is it with gadolinium in addition?
I think it's gonna be more or less the same thing that happened in Super K. They're gonna run first with just pure to water,
Yeah, but
and then at some point they're gonna dump in the
They will
gadolinium.
switch.
Yeah, because
Yeah.
what you probably know, when you dump it in,
Mhm.
you have this more sensitivity towards lower energies, right? And they want to look into that as well. Yeah.
Yeah, okay.
Yeah.
Thanks.
Other questions? I actually had a question. So I know from IceCube Gen 2 that is a huge effort to test all the all the PMTs
From where? Sorry, say it again.
from IceCube Gen 2
IceCube, okay.
discussions. How do you actually test and calibrate all the PMTs, or do you just trust that they work?
Oh, well, there's several things you could do. The
Do
first,
you do it manually?
well, like ourselves would setting up you know, you might know this. You do a block box, right?
Yes.
And you put a PMT inside, and the first thing you do is you do a single photo detection,
Yeah,
right?
and you do that manually for all the 20,000
Well, probably they're not gonna do all of them, but you know, there is this. I remember from college, you had this friend and this girlfriend that you know, if you work at airport and you have this big shipment from, I don't know, 10,000 doors, right? You take just a percentage of that, evenly distributed, and that tells you whether the distribution is okay,
Okay.
right? I guess so. Yeah.
Thanks. Online question? Yes, please speak up. If you have a question.
Lot of appreciations for fruitful and wonderful discussions, professors. Really great.
Can you repeat the question? What is the sensitivity? Thank you.
Thank you.
All right. I don't see any other questions. Then let's thank Saul again. And the next speaker is Lucas, who will, I hope, give an update on the status of Corsica 8.